Okay, so welcome back. Happy Wednesday. We are continuing with what we started last class, which was lesson number 7, polynomial optimization problems. Just a heads up, looking at the next few classes. On Friday, our first quiz is assigned. It is a take-home quiz. I will give it to you Friday. You will work on it over the weekend and hand it back to me first thing Monday. You don't need to study for the quiz per se. It's open book and open note. But just doing your homework consistently is the best way to prepare for that quiz. Also coming up, the 2 projects that hopefully you are making good progress on. Arbitration is due on September 28th, and trucks is due on September 30. And Friday coming up is our project check-in day. So on Friday, we're just going to come in and work on the projects with your classmates and with me and with whatever. Any questions on the calendar? Okay, so again, on page 47, when we last left off, we finished page 46. We're actually going to do page 47 right now and then just take a quick look at the conclusion from page 46, and then you'll do the activities. Number 9, here's our first of many optimization problems. The key word there is optimization. Optimize means to make as good as possible. So this collection of optimization problems, you're going to see them threaded throughout the course, and the goal for every single one of these optimization problems is to make some function either as big as possible or as small as possible. We're looking for the best or worst, highest or lowest, the optimum, whatever that means. A math book is to contain 36 square inches of printed matter per page, with margins of 1 inch along the sides and 1.5 inches along the top and the bottom. Find the dimensions of the page that will require the minimum amount of paper, and find the minimum amount of paper. Okay, and then there's other stuff we're going to do too, but let's just start by drawing a diagram and see if we can understand what's going on here. So there's the entire page, but we know we've got margins all the way around, and so inside of that page, I'm going to draw a smaller rectangle, and that smaller rectangle is where we find the printed material, okay? The text is in the smaller rectangle, margins around the sides. We'll label those margins. It says 1 inch along the sides. So here to here is 1 inch. Here to here is also 1 inch. And then on the top and the bottom, it says 1.5 inches. Okay. And there's a hint here. It says let L and W be the length and the width of the part of the page that is printed on. So we're going to say that we'll call this guy right here in blue W. And we'll draw some green here. That thing right there is L. And we are given the fact that the book is to contain 36 square inches of printed matter per page. So that's an equation for us, right? What's the equation? Yeah, what about the 36? Yeah, 36 equals what? L times W, right? That is the printed matter being 36 inches. Right? How many different solutions are there to that? How many different rectangles have an area of 36? Infinitely many, right? It could be like 36 by 1, it could be 9 by 4, it could be some crazy decimal times some other crazy decimal. Infinitely many solutions to that. What we are after is the best solution, meaning the solution that makes it so that the dimensions of the entire page, not just the text part, but the whole page is minimal. We want to find the smallest page that we can that will still get 36 square inches of printed matter on that page. And you could imagine, I'm going to draw something and then erase it real quick. You know, imagine a 36 by 1. 36 by 1. It's got 36 inches of printed material there, 36 square inches, I should say. But then it's got the borders, same borders as before. What do you think about the area of that one? Do you think it might be the smallest one we could find? To me, that looks like a pretty darn big piece of paper that we're going to be using there. Big meaning lots of area altogether. The area inside that blue rectangle is fixed. It's going to be 36 inches, square inches. We're not changing that, but throwing the margins around there, I feel like we're wasting a lot of paper if we do this. And so then maybe we start to think about, like, making it a little bit shorter, but then wider, and then someplace in there is the best one. So that's the goal of this problem. So let us write a formula. We're trying to find the minimum amount of paper. That means we're looking at the area of the whole page. And we're writing a formula here. So the area of the whole page, well, it is a rectangle, so it is a length times a width. What expression for the length of the whole page? L plus 3 is good for the length of the whole page. Length of the whole page is the green L plus the 1.5 inches on the top plus the 1.5 inches on the bottom. L plus 3. That is the length of the entire page. Go ahead and write down the width of the entire page. It's going to have W in it. What is it? W plus 2. Everybody buy it? Blue W plus an inch plus an inch. W plus 2 is the whole width of the entire page. And so the area of the whole page, I think we've got it. It's the length of the whole page times the width of the whole page. Everybody all right with that? Okay. How many input variables are there in this formula? Input variables. There are 2. There's an L and a W. That's no good. In Calculus 1, all of our functions are going to have a single input variable. 2 semesters from now, many of you will be in Calculus 3, which is happening right on the other side of that wall right now, where you will have more input variables than just one. But here it's just the one. And so what we need to do is change it. We got to replace something in here so that it's only a single input variable. And we're going to use that highlighted equation to do so. We're going to do substitution. We're going to solve that highlighted equation for one letter and substitute it into this formula for the whole area. So let's go ahead and solve this guy for L. Doesn't matter which one we solve for. But divide both sides by W, and we get L equals 36 over W. And then we can take that thing and substitute it right in here. So I'm going to copy most of this. I've got copying everything except that L. Instead of L, what can we put? 36 over W. How many input variables now? 1, which is super, because we are in Calculus 1. So we can handle this. All right, I have a function for the area of the whole page. It has 1 input variable here. The way that we are going to find the minimum value of this function is to use the techniques we saw last class. If you are imagining a curve, like imagine a parabola, y equals x squared, what can you say about the tangent line at that minimum point? It has a slope of 0, right? It is horizontal, and so that's what we're after here. Even though I have a hard time visualizing the curve that is this equation here, the area function, maybe goes up and goes down and goes back up. I don't know, but I'm just looking for that place where it's at the bottom and it's going to have a horizontal tangent line. So our technique is going to be very common this semester. Take the derivative of this, set it equal to what magic number? 0, because that's going to find us the places where the slope is 0. So to find the derivative of this thing, I got to do some rewriting. I can't take a derivative of this right now. What's our algebra technique first? FOIL, or distribute. Right? So let's do all this foiling or distributing here. Okay, equals. All right, so what do we get here? First times first is 36 plus outers. 72 over W is good, right? Just multiplying the outers. Inners is a plus 3W. And then the last is a plus 6. Okay, there's our FOIL. Okay, and then, yeah, let's just combine the 36 and the 6. So 42 plus, and then I'm copying everything else. Okay, so there's our area formula, cleaned up as much as possible. And now we're going to take its derivative, set it equal to 0. So taking its derivative, what's a good name for this formula that I'm about to write? A prime. That's it. Right? We had an A, now we have an A prime equals. Okay, the derivative of 42 is 0. It's constant. 72 over W, we can't apply the power rule, but this is one of those shortcuts that I recommended that we memorize. A constant over X becomes negative the constant over X squared. So what's the derivative of 72 over W? That's it, negative 72 over W squared. Looks like magic until you memorize that formula, and then it's just easy. Plus 3W, derivative of constant times X is just the constant, so the derivative of 3W is just 3. Okay, that is the slope of the tangent line. Thinking of this area function, maybe going up and down, we've got our slope function. We want to take that and set it equal to 0. Technically, we also should be thinking about places where the derivative does not exist. Remember we had that picture with the kind of corner at the bottom point. So it's possible to have a bottom point or a top point where the derivative doesn't exist. And in fact, there is a value of W for which this derivative doesn't exist. What is it? 0. But having a width of 0 means the piece of paper vanishes. And so clearly W equals 0 is not the solution, right? Because it just doesn't make sense in the scope of the problem. But it is something to consider before we toss it out. So it's usually what we're going to be doing is taking derivative and setting it equal to 0. But also we need to think about where the derivative doesn't exist. Okay, so let's take this derivative and set it equal to 0. I'm going to add that fraction to both sides, and I get 3 equals 72 over W squared. I don't like my variable in the bottom, so I'm multiplying both sides by W squared. Divide both sides by 3. What is that? 1, 4, 14? No, 18? What am I doing wrong? 2, 24. That's it. Am I wrong? I have no idea what I was doing. But some people think that I come in like with the answers memorized and then they're not impressed when I do stuff in my head. So my ineptitude right there should prove that I do not come very prepared with those calculations memorized. Okay, and then we solve for W by taking the square root of both sides. So we get W equals the square root of 24. We'll go ahead and simplify that. Let's see, so what nice number goes into 24? 8 goes in, but 8 is not super nice inside of a square root. So 4 is a good number, right? So the square root of 4 can come out as a 2 with the 6 still in there. 2 root 6, that's good. Another technicality, W squared equals 24 has a solution, has another solution. What is it? It's the negative of this thing. But having W equal negative the square root of 24 also doesn't make sense because the width has to be some positive number, okay? So we consider it, and then we ignore it. Okay, 2 radical 6, that's the width. Now, what we know, again, imagine this area function, maybe it goes up, maybe it goes down, based on picking different widths. We know that if the width is 2 times the square root of 6, I did that division right, didn't I? 3, 7, 2, 4, yeah, okay. So if the width happens to be 2 times the square root of 6, which is just a little less than 5, so imagine 5. So if the width is 5, then I know that the slope of my tangent line is 0. Does that mean I'm at a minimum point on this curve that I'm imagining? Yeah. What is it? Is it definitely a local minimum? Is there any other possibility if that tangent line is horizontal? Josh? Couldn't it be a local maximum? Couldn't we be finding the worst possible point? Just imagine a curve that goes up and down. All we know is that the tangent line's horizontal, but we don't know that it's definitely the kind of horizontal we want. We want a minimum, but it could just as well be a maximum. In fact, it could be nothing. Remember our example of y equals x cubed? At the origin, it's definitely horizontal, but it's not a min or a max. So just because we've got our value here doesn't mean that we've finished. We still have to make sure that it indeed is a min. So here's how we do it. In the problem up there, we didn't read this part, but it says we're going to do our first sign test. So here is our first sign test. We are going to put that number, 2 radical 6, right here on a number line. I'm also going to put 0 because negative widths have no meaning in this problem. So there's definitely a cap here on the left. And there's actually also a cap on the, is there a cap on the right-hand side? 36? Oh, no, maybe there's not. Yeah, okay. All right, so I think we're good here. Like you could pick a width of 1,000,000 inches and you could make a really wide and you know, like teeny tiny like height rectangle that's a 36 area. Okay, and what we're going to be doing here is making a sign chart on the derivative. So I'm going to label that guy with an A prime. And so we're going to say a lot and write down very little. Hopefully we can follow along here. What I'm going to do is pick a number, any number in this interval, 0 to 2 radical 6. 2 radical 6 is about 5. If you're not sure of that, you can just type it in. So we're just picking a number between 0 and a little less than 5. 3, super. That's clearly inside of that interval. We're going to take that test number of 3 and we're going to plug it into A prime. Let's see, so A prime is up here, this purple guy, negative 72 over W squared plus 3. So we're going to plug in the 3 here. So I got negative 72 over 3 squared plus negative 72 over 9, which is negative 8. Plus that 3 is negative 5. So when I plugged in Matt's 3 for W, I got negative 5. The important thing is that it was negative. And you might be wondering, well, what if we picked a different number besides 3? Well, the fact is any number that you pick in this interval and plug it into the derivative for W, it is going to be negative. Any number you want. It's kind of surprising until you sort of think about how we came up with that 2 root 6. I'll let you play with that. But for example, if we had picked W equals 1, which is also inside of this interval, what do we get here for the fraction when W is 1? Negative 72 plus the 3, negative 69, still negative. Wasn't the same negative we got before, but it's negative. And then we pick a number bigger than 2 root 6. 4 is not bigger. 2 root 6 is around 5. 6 is fine. 7 is fine. My standard is 100 because I don't want to make any arithmetic mistakes here. Remember, we're not doing a calculation. We just care about the sign. I'm going to pick 100. If you pick 100 and plug it in for W, this negative 72 over 10,000 is really close to what? 0. Really close to 0. It's negative, but it's really close to 0. And then I add 3. What kind of a number am I going to get? Positive. Also want to point out, I did not write 100 on the number line. I didn't write Matt's 3 on the number line. I didn't write 1 on the number line. The only thing that belongs on that number line are critical numbers and then endpoints like 0 if there's like some context to the problem. Putting other numbers, these test numbers on there can only lead to confusion. Don't do it. Okay, so here's what we know. We know that the slopes of the tangent line for this area curve I'm envisioning are negative until we get to this 2 root 6 and then positive. So just imagine negative lines like this and then positive lines like this. Yes? What kind of a point am I looking at? Is that a max or a min? That is a min. And that's how we know for sure that we've got indeed a local minimum. In this case, it's a global minimum because it's the only thing. Function goes down and then goes up forever, the bottom point. Okay, so here's the required justification that is typical at the end of a max or min problem. Since blank goes from blank to blank at blank, blank has a local blank at blank, which reminds me an awful lot of junior high school when we used to film those Mad Libs when the teacher wasn't paying attention. So don't write the word toilet in any of those blanks. That's okay. Here are some choices. You're not always going to have the choices written out for you, but let's try it. Since either A or A prime goes from positive or negative to positive or negative, A or A prime, what was the thing we did the sign test on? Was A prime. Got to put the right thing in there. Since A prime goes from, okay, so on the left-hand side it was negative. On the right-hand side it was positive. At, and then you tell me the value of the independent variable. In this case was 2 root 6. I'm going to put the letter W in here as well, just to be clear. Oftentimes it's an X or a T, but just put, since it goes from negative to positive at W equals 2 root 6, blank has a local max or min. Which function has a local max or min? A or A prime? It is A is the thing that has a local min. A. Because the slopes of the tangent lines are what we just analyzed. They were slopes of tangent lines of A. A has a local which one? Min at, and then we'll just copy that same W equals 2 root 6. So writing that justification isn't all that long, and with some practice you'll start to get the format. It's always this format, but it's mandatory because I'm looking for a minimum point, and 2 root 6 could have been maximum, could have been the absolute worst thing we could have done, right? Just by finding a horizontal tangent line doesn't mean you get what you want. Just means you get maybe a min, or maybe a max, or maybe nothing. Okay. Any question? What's that? A W is just the width. And so I think we need to finish this problem by finding the length. What's that, Mahendra? Yeah, so we want, what does it ask for? It wants the dimensions of the page, so we're going to find a length and a width, and it also wants a minimum amount of paper, so we'll find that too. So this is us wrapping up this problem. We know that W equals 2 root 6. We have a formula that says L equals, what is the rest of that formula? 36 over W. So now 36 over 2 root 6. So reduce that guy just a little bit. Actually, I think we can clean this up even more. You guys remember the technique to rationalize a denominator? Top and bottom get multiplied by root 6, right? And so I get 18 root 6 over root 6, right? What's that? Yeah, so over 6, and then 18 over, I'll just write it. So I think that just becomes 3 root 6. So we've got our best width, we've got our best length. We can go ahead and find the best area too. Area equals. Okay, so I know area is length times width. Can I just multiply these two numbers? We're looking for the area of the whole page. We need to add. What do these numbers not include? All the margins. In fact, if you multiply them, it doesn't take long, but let's confirm that it makes sense. If we multiply these, the 2 times the 3 is 6. The root 6 times the root 6 is 6. So 6 times 6 is 36. So indeed, this is one of the infinitely many rectangles that have an area of 36. But now we get to tack on the margins. So it said L plus 3 and W plus 2. And you actually have to be careful because you got to add the 3 to the right one. You don't get to just arbitrarily add 3 to one and 2 to the other. Okay. So then the area is L plus 3. 3 root 6 plus 3 times 2 root 6 plus 2. Okay, got that right. Okay, so I'm sort of tired of doing calculations with root 6. Can somebody just get a calculator and we'll get a decimal on this guy? While we're waiting on that decimal, any questions on this problem? Yeah, Josh. What's that? Oh, you have the answer. Please. One is fine. 71.4, 79.4, 71.4. I think square inches for this guy. Minimum amount of paper. Change the original rectangle, you'll be using more paper than this 71.4 square inches. Okay, standard process that we just followed for optimization problems. Actually think, is this written up anywhere? I feel like I've seen it someplace, but now I can't remember where it is. You have a function that you are trying to minimize or maximize. Oftentimes it's given in words and you need to translate that into symbols. Typically, that function is going to have more than one variable in it. Our job is to do some substituting to get it so it's just one input variable. We originally had L's and W's inside of our area function. We changed the L into 36 over W. So in order to do that, you need to create some other equation that allows you to do this substitution. Once you've got your function to be minimized or maximized with just one input variable, we take the derivative, we set it equal to 0. Occasionally, there's also places we need to think about where the derivative doesn't exist. We solve for the critical number. In this case, it was 2 root 6. There could be many critical numbers. You do your sign test, and you make your sentence with the conclusion. That's the whole process. These are tough problems. The reason these problems are in chapter 4. Okay, last thing here, and then we'll do the activities. The ideas behind our sign chart above are formalized in the following theorem, which is called the first derivative test. Soon enough, we will have the second derivative test. Suppose f is continuous at a critical number x0. x0 was what number in this problem? What was it? Was the value of w, is it I forget it already, 2 root 6? 2 root 6, yeah. So that's our critical number. If f prime of x is less than 0 immediately to the left of our magic number, and f prime of x is bigger than 0 immediately to the right, I always have to think about this. That's just a lot of symbols for me. But f prime is less than 0, downhill tangent line, and then uphill tangent line. What are you looking at x sub 0? Is a local minimum. F has a relative minimum at x0. Part B, if f prime is positive immediately to the left, what kind of tangent lines? Positive, so uphill tangent lines. And then f prime is negative immediately to the right, downhill tangent lines. Then what are you looking at? A maximum. And then part C, if f prime has the same sign on both sides of x0, so maybe it's positive to the left and then positive to the right, just briefly horizontal. What are you looking at that spot? Min or max? Nothing. It's neither, right? And then other way, if it's negative to the left, briefly horizontal, and then negative to the right, still neither, right? So you might have a sign test where it's plus plus. Your conclusion is no max, no min, nothing. So that's what it says there. Okay, and then I've got this little note here really to remind me to just go back and remind us of this process we followed. I had to kind of rush it at the end of last class, so I just want to point out something we did. It said find the absolute extrema of that formula on the interval 1, 5. That means the absolute highest and absolute lowest points. So here was our process, very standard calculus problem. It's, I think, the second one in the activity today, is to take the derivative, set it equal to 0, solve for x, these are your critical numbers, and then you make a sign chart. The sign chart has to include two kinds of numbers. What are they? What are these? What is 2 and 3? We will, yeah, so we got to find these critical points. They go in the chart, and we have to also include the endpoints, 1 and 5 in this case. And then we plug all of those into, not the derivative, but the original function. We did that on the calculator over here. And all you are looking for with this collection of y values is the highest and lowest points. Those are your minimum and maximum points, all right? So that's your process. It's a dead giveaway when you've got this closed interval given in the problem. Okay, skip ahead 2 pages, and let's see how far we can get in the activities.